Hey guys, how's it going? Welcome to another episode of Ferris Makes Hardware. This time we're working more on the xenowing. I called this episode DDR3 testing, but it's actually a bit more than that, just because that's sort of the last thing I was working on. So to catch up a couple things that I did in the last week is, I think last week I was talking about how I was really excited about that I basically figured out this really nice testable architecture that I was really happy with. Still pretty excited about that. I think that's the way that this project is going to go. I think it's the way forward. And that got me so excited that I wanted to start working on the actually getting the rasterizer into RTL. And as I was sort of preparing the rasterizer, in particular, I was kind of massaging the code so that I could sort of move more and more of it to fixed point. So I can pull this up. So the rasterizer now, it's still like all this stuff looks the same, where it figures out all the interpolants that's gonna interpolate across the triangle. Except now a lot of these are in fixed point right now, and of course this relies a lot on just like everything before this triangle setup is still floating point, and I'm gonna kind of propagate the fixed pointness backwards still, or the fixed pointness, if that's a way to put it. And I haven't done any of that. I'm just still doing all of that in floating point, and then at the very end converting it to fixed point, because what I'm thinking is that pretty soon, once this whole inner loop part here, which is the actual rasterizer itself, is all fixed point, then I can start separating that in software a bit more, kind of isolating that, and then start moving that over to RTL. And I might even replace the software implementation with a Verilator simulator, but I need to consider a few things before I try that. Anyway, what I tried to do then is I was reducing, in addition to going to fixed point, one of the things that I thought that I was going to have to do based on some earlier tests that I had done on the old board, I had kind of calculated that I would spend like 15% of the time per frame just streaming out pixels, even if I did 320 by 240 with 16-bit color. So knowing that I was going to do fixed point, one of the things with fixed point that you have to be careful with is you have to decide how many fractional bits you'll use for different kinds of values. So you can see here I use 8 fractional bits for these edge functions. I use 30 for inverse W, 30 for Z, 24 for S and T. And these I just kind of tweaked based on the demos that I've been testing with until it was okay. And all of these are like chosen specifically for different kinds of parameters based on what those kind of parameters would tolerate. And so the point I'm trying to make is that it's important that you know the kind of range of values you're going to be operating in. And when I started moving the color math and everything over to fixed point as well, I had to decide like how many fractional bits is used within that also. And so I started moving everything to 16-bit. I moved both the textures and the frame buffer to 16-bit, and it looked so bad. Like it was really disappointing. Another thing that I did is I also dropped the max texture resolution to 128 by 128, and again that's just like you do some back of the napkin math. So if we do 128 by 128 by 2 bytes per pixel, and we have 32k of cache just for the textures, which on one hand is kind of big for the FPGA. It's not huge, like this is not really an issue, but it's kind of big. On the other hand, we have to move that in and out of the texture cache, and that might take a long time. So that's already fairly large, and then 32 bits per pixel would be double that. So I just kind of had chosen those parameters, and I was moving everything, and it looked so bad. I don't even want to show it because also I already reverted a lot of those changes. But so then I when it looked that bad, I just kind of thought, do I actually need 16 bits? And so I went and I sat down, and finally, after putting it off for a long time, I went and wrote a test for the DDR memory. And in particular, let me pull up the code here. Yeah, so I use the Altera's MIG, which is memory interface generator. And for this particular board, it actually only gives me one, or at least I can actually, I guess, clock it lower, but it gives me a very particular max value for the clock for the memory, which is 400 megahertz. And then the user interface that it gives me for that is 100 megahertz. So I can't interact with the memory interface any faster than that. But I thought, okay, that's fine. And I can do 128-bit words at most, one per cycle. Definitely going to be less than that. So I just kind of wired up a test to test that out. So these are DDR signals. There's clock and reset. And then I also hooked up a LED to make sure it was working in the UART. And essentially what this test does is it bootstraps the memory controller. And then once that's working and calibrated and everything, then it goes through and it writes the entire 256 megabytes, which is how big the memory is on the board. So it writes all of that, and the whole time as it's writing all of that, it increments this word counter, or actually this write cycles value is the one I'm trying to point out. And then once it's done, it sends that as an 8-byte value over UART. So I can have a program on my PC running. In fact, let me show this. We could just actually run this thing. It's not turned on. There's my device, and this tool that came with the board is a piece of crap, so I have to restart that. Oh no, there it goes. Let's see. So I'm going to first open this. So in here there's the folder for my board, and then there's a test folder, and there's the DDR3. And in there's a MISC folder with this DDR3 check tool. And this I just threw together in Rust. I have a few of these in the repo now. And they're really basic. Let's see. It's literally, because the UART ends up being a COM port on my PC via USB. So I just set up the port name and the baud rate. And in this case, I just wait for whatever I need to wait for. So I know the test is going to send a 64-bit value for the write cycles. And then it's also going to go back and read all that memory. And it's also going to cycle count, and it's also going to check that the values were the ones that I wrote. So let's see. If I do cargo, run, I think comp5 is the one. Then this is running, and then if I reset, or if I load this onto the thing, so let's run this. When this finishes, you should see this stuff pop up. And there it goes. So we see to write out 256 megs of memory was this many cycles, and to read them back was this many cycles. So in total, it was this many cycles. So this is around, what is this, 38 million or something, which is about 0.38 seconds because it's 100 megahertz clock. So then what I did is I went and I just made this spreadsheet here. And let me see if I can zoom in a bit. I'm not trying to insert. Let's zoom in. Okay. So the whole thing here is we plug this in. These are the cycle counts. You can see it's also, this is kind of surprising, it's slightly faster to read than to write, which I don't really get that, other than the fact that a write is like a read modify write with DDR. So that's probably all it is. But I don't know. I haven't really looked into it. And then I just did a bunch of calculations. So I put in the system clock here and then a bunch of parameters that I was kind of toying with, and then just set up really basic formulas for these, just so I could play with a lot of these values and see kind of how they're interconnected. So if you plug in these cycles, then you divide that by the clock frequency, and you get that it was this much time. And since we know that our word size is 128 bits, and we know that our data is 256 megabytes, then we can do calculations about our data rate. And so this is our data rate. That's literally, I think, what was B5 again? Yeah, it's literally our amount divided by 1024, so it's in gigabytes, and then divide that by the time it took to write it or read it. So we get about 1.26 gigabytes a second and 1.36 gigabytes a second for reads, 26 for writes. And then I also translate this to gigabits, which is just that times 8, I think. Just because, why not? I think actually, because they talk about like mega transfers a second, and I guess this would be giga transfers a second. Or the transfers are 128 bits each or something. I'm not actually sure how that relates, to be honest. But actually, it doesn't really matter, because the most important metric is here, which is this how many cycles we spend per word that we can read or write to the controller. And basically, this can never be below 1, because that's the fastest we can clock our system. We'll never get more words per cycle. And this looks really good to me, 1.18 cycles per word and 1.08 for reads. Now, first of all, we're never going to get like below 1 because that's logically impossible. But also, we're probably never going to get to 1 because one of the things that DDR has to do is refresh. And the controller takes care of that for us. So we should expect that sometimes the controller will spend time doing that. Now, I didn't really calculate how much time this is that would have had to go to that because I don't really care. I'm satisfied with these numbers. But I look at this and I think, okay, this is probably about the best performance we can get. And this makes sense too because the test itself is as minimal as it gets. It's literally writing the whole time. It does have to do some complicated stuff just because the way that the memory controller interface works is not quite how I expected. But that's also what kind of made me comfortable about that this is kind of the best performance that we can get, because I went through a couple iterations of this, and right now this code has some duplication in it, but that's in order to not have any like accidental wait states. You guys can read the code on the repo if you're curious about that. But yeah, so it literally just tries to write every cycle that it can, and then when it's reading, it literally just reads the whole time. And in fact, it even separates the like waiting for the return values from the reads and checking those as a separate block. So this one's just waiting for data to come in and then checking that it matches. And then eventually it's going to mark if the read check is done and then if it passed. And so this one's just sitting here and issuing reads the whole time. It doesn't even wait for them to return or care about that, because I think I measured like 25 cycles latency for this, which I actually should probably put in that spreadsheet. So it's about, I can read or write, like the throughput is one read or write per cycle about. It's a little bit less than that. But the latency is about 25 cycles, which is kind of a lot. But I kind of knew that too. That's one of the reasons why I'm going for an architecture with a bunch of separate, really fast local memories for all the different blocks. Is to separate it from that kind of latency. But this way we get like as high throughput as we can, where we're just issuing as fast as we can, trying to reach one issue per cycle. In practice, getting a bit less than that as we expect, and then having it check as often as it can as well. So I think at the end of this, it sits there and just issues reads the whole time, and then after the final read, it waits until the checker's done. And if it passes, then we're good, and it transmits the read value. Otherwise, it goes into an error state, and then it doesn't turn the LED on. Maybe I should have made it flash or something, but it doesn't really matter because it works. So in fact, if I go, it's still running. So if I go ahead and reset on my board here, it'll do this a couple more times. And this is stable. You see the same counts every time, because whenever I hit the reset, it resets the memory controller as well. So from a rest state, it's going to do the same logic every time. So we're going to see the same cycle counts every time. So if I wanted to, one of the ways I could improve this test is I could like make it also take in commands from UART, and I could make this tool on my PC send a bunch of different commands and then like get averages for these cycle counts. But I don't really care. Again, I'm really pleased with these results, so I don't really feel the need to test this, do more targeted testing on this. So that's pretty cool. But then we go and start looking at some of these other values, because once we have these numbers, then actually we can calculate a lot of really cool stuff. So for example, if I have a 100 megahertz clock and that kind of data rate, and my screen width, I want it to be maybe 320 by 240 pixels. We know how many pixels that is. We also know our target frame rate. So we have our number of cycles per frame, which is just based on the system clock and the target frame rate that we want. And this is kind of where it gets interesting. If I want to say, like, originally I was thinking about a 16-bit frame buffer. So as you can see, when I change that, this recalculates, like, this is how many bytes per frame that is the back buffer. And this is important because we actually have to stream this out to the display, to the HDMI transmitter. And so we can see this, it would, for this many bytes at this rate, it's going to take us this many cycles per frame. And in practice, it's going to take us a little bit more than this, because we're going to get hit by that latency at least every scan line. That shouldn't be too bad, because it's only like 200 times 20 or something. So it's not really significant. But that is why it says min. And then of course that as a percentage of the amount of cycles per frame we have is 0.62, which is actually a bit lower, because I was expecting to spend like 15% of the time streaming out pixels. And where that number came from is because I expected that I wouldn't be able to, I didn't know that I was going to use like whole line buffer. So I didn't know that I was going to be able to achieve max throughput here. I thought I was going to have to do issue writes, and then I would assume that I would always take the latency hit, but it looks like we're not gonna have to do that. So this is actually much lower than I thought, which is great. But not all of these work out to be that great still. So for example, with this color depth and this amount of precision for the depth buffer as well, which is now something that I'm architecting around, which didn't used to be, but now it is because I think we can afford it. I think that's more fun. I can also figure out, since I know I'm going to do a tile render, this is going to be the width and height of the tiles. And again, based on that and based on this information, it's going to take this many bytes to transfer. Essentially, this is our tile memory size. I think I'm actually going to use double this for some reasons I'll get to once I get the rasterizer working in RTL, which may end up being the way I do it. So we'll see. But essentially, you need to transfer, like, I guess this is where it gets more interesting to me, at least. Once we have a lot of these numbers, like, we can start judging what our performance of the system is actually going to be. And one of the things I actually want to do is take some of the demos I'm testing with and just freeze some of the frames and capture actually what data is going to go to the GPU for that. So I can get more precise statistics. But I just thought, okay, well, what's the worst case? The worst case is the user draws a bunch of blended triangles that cover the entire screen. So if you have a full screen quad or something, and we're just considering the rasterizer itself, we're not considering like polygon setup. So poly count and how much of that setup time we spend and how many draw calls we have and how many vertices we have, that's obviously going to play a part as well. But just looking at this in isolation, we can already make some interesting, draw some interesting conclusions. So for example, if we're going to draw something that's a full screen quad, we know we need to do this many tile transfers just to move the data in and out of the rasterizer. So this doesn't even consider the actual time drawing pixels. This is just how many of these length transfers we have to do just to move data in and out of the rasterizer. And so then you can extrapolate that. It's this many bytes times this many transfers. By the way, this should be 300, but it's times 2 because we need to move the data both in and out of the memory. So that's why it's 600. And then of course that corresponds to 0.6 of a megabyte or so, 60% of a meg. And then we can also calculate how much of like the percentage of the frame time that would take. So this is only 3%, which is not too bad at all. Which means we could do this. If we just did a bunch of tile transfers, we could do 22,000. And then if you put that over the whole screen, you get 36. So at this bit depth, we could basically cover the screen 40 times. Assuming the rasterizer was fast, again, this doesn't take that into account. But it's like, I think it's really cool that we can even do these kind of estimates. So of course, this is higher than I expected. And I also expected to do 16-bit textures. And I basically did the same here at this bits per pixel for the texture and this max dimensions for the texture. Then the worst case is that for every draw call, we have to do this, transfer this many bytes, and we can do that 700 times a frame or something, which is, again, better than I expected. So I just decided that I'm going to crank this up to 32. And again, as I do this, you can see this changes. So now we have to do 64K, which we could do 350 times. We're not going to need to do it that many because we're not going to do this many. We're not going to do 300 draw calls with 128 by 128 by textures. So not worried about that. And then here we can see that, of course, this number of bytes doubles. Now the bytes per tile transfer doesn't actually double because that's also based on the depth bits, which we kept the same. If I had 0 here, for example, then this would be a lot lower, but I want at least 16-bit depth, and I'm actually considering doing 32-bit depth, but I don't think I will. So then we can do 600 of these for the whole screen, and that amounts to a bit more. Is almost a megabyte, and then we're at 4% of the frame just moving the data in and out for one draw call that covered the entire screen, which then it's getting a bit heavy, but I think this is the kind of performance we're targeting. So then I could do that only 14,000 times per frame, or I could fill the screen 24 times. Again, this assumes a rasterizer that takes no time, which is not what we're going to have, but this number seems to be kind of ballpark. And that also seems pretty good. So then I also wanted to look at, like, what if I want to do 640 by 480? And then things start getting a lot lower. So for example, I could just considering moving the data to and from the rasterizer, I could only do that 6 times per frame, which that might be okay because we're probably not going to draw the screen the whole time. So maybe I end up doing 640 by 480 in the end anyway. And then here we're back up to like 16% of the frame time just going to streaming out pixels, which is kind of where I started with. So it's kind of funny how this scales. It's in a bit of non-obvious ways, but basically I just got sick of doing a lot of these calculations trying to do them in my head and failing, and then doing them in a calculator over and over again. So I just stuffed them in a spreadsheet. And I'm really happy with this now because I can sit here and play with these numbers, which is, at least to me, feels really nice. It's nice that we have an architecture where the performance is going to be not quite this predictable. Again, these are all best case, and they assume a rasterizer that takes no time, and they assume that the triangle setup takes no time. So having a lot of leeway in this is pretty good. So then the other thing is, what does that's great that we saved us from having to do 16-bit color. But what about, how does everything look at 320 by 240? Because I've been testing this test render at 640 by 480. So what I did is I hacked GL viewport to divide everything by 2, because all the test demos I was doing was 640 by 480. So if I just break this on the input, and then I also scaled the output window just using mini FB here. So I turned up the scale. So if I run one of these test demos, for example, liquid when by HowJob, you see this actually doesn't look too bad at all. In fact, I'm actually getting kind of excited by this aesthetic. So there's obviously some bad things here, because a lot of the textures in this demo are 256 by 256 or 512 by 512. Whereas now I've added a hardware limit to 128 by 128. And so I end up downscaling the textures when they're uploaded to GL here. And I just did a really basic linear downsample, so they get kind of blurry. So if I did actual proper 128 by 128 textures that were sharper, if I like prepared them in Photoshop or something, this would look a bit better. But I think overall it still looks pretty good. But with a lot of the full screen overlays, you'll see these like dark lines in the middle of the screen. And I think that's due to the fact that I just and the bits if they're not exactly powers of 2. So there's some bugs there, but that doesn't matter, because it's not a bug in the render. It's just some corners I cut in this test front end. So I think I'm okay with that. But very soon I want to do my own content against this renderer as well. But yeah, I'm talking a lot. But I'm just really excited because now we kind of know roughly what kind of performance we should get, at least out of this part of the system. One of the things I really want to do soon is also work on a vector unit for doing vertex transformation, which I think is going to be really fun, but haven't started on that yet. But yeah, I'll just let this play because I kind of like watching it and thinking about that this is kind of what our stuff's going to look like. I mean, there's like one of the big inspirations for me for a lot of things is Ocarina of Time, the Zelda game for N64, and that also was 320 by 240, so I feel like if they can get away with it, so can we. Yeah, so that's a good question, Dark Second. Am I going to use my demo tool for xenowing content? I don't think so, because it's not really appropriate. It's really shader based, our current demo tool, but I have been thinking about using it as an excuse to develop like a branch of the demo tool. In particular, I would really like to work on our node-based stuff, and that would be a really good way to dog food that, like to make another kind of scene graph that's specific for this kind of content, and also an animation system with their own curves and everything is something I've wanted for a long time. So I think maybe it's a good excuse to kind of develop those more or less in isolation against an engine that's specifically for this. Maybe. I don't really know. I'm not entirely sure yet, but that's something I'm thinking. So we'll see. Because an engine for something like this is going to be a lot more limited by nature. So I think it needs to be targeted for this, but things like a timeline or a node editor are going to be general enough that I think I can start with those. So I also think that sounds fun. But the next sort of intermediate goal is that I still want to, so in parallel, I'm doing all this like targeted RTL testing. So for example, I did this memory test, and I also want to see if I can improve the rate of the UART that I'm doing. I could also look into other links just to reduce or increase the bandwidth between my PC and the device here, because I would really like to, I think like one of my next goals is to get this demo, for example, running against the hardware on the FPGA. So This demo will never run on the xenowing because it relies on Windows and a lot of other stuff. But I think it could run as long as I hook up to the FPGA via UART and just move all the data in and out. So it'll use the same rasterizer. So essentially just using the FPGA as a GPU and streaming data to and from that instead of doing it all in software. So I think that's like my next big goal. And there's a lot of small goals on the way to that, but I think that's doable and I think that's reasonable. The only problem is I think it's going to take about 10 seconds per frame right now, just based on it might even be a lot worse than that, but just based on the fact that I have very low bandwidth via the UART. And I think I can increase that. The chip's supposed to handle a lot more than what I'm using right now. And I did bump that up a couple times before, and then I hit a wall somewhere and didn't really look into it, but now I have more of an incentive to look into it. So actually maybe that's what I'll sit here and play with for a little bit today. Because it would be pretty sick to be able to compare the software and the initial hardware implementation side by side. And I think that's going to be a great way to debug it as well. So I'm really looking forward to that. And even if I only render like part of the screen in order to make testing faster, that's still viable to me. So that's another thing that I have to do with the software renderer is I have to get everything to fixed point, and then I have to actually make it a tiled renderer. So I'll do some kind of basic form of binning and triangle preparation and stuff like that. So yeah, should have a USB controller. That'd be cool. I could modify because I think this I don't remember if these demos are relying on GL for producing the projection matrix. If they are, then I could actually bake a view matrix in that as well that I could control via a controller. That'd be fun. But yeah, for testing this, the bottleneck is totally going to be the UART. It's really slow, which I'm okay with as long as it still lets us test stuff. But in that case, I probably wouldn't run it against a demo like this. I'd probably make a couple test scenes, even if it's just a cube rotating around and stuff. That's still helpful, and then I don't really care if it takes 10 seconds to render if it's just going to do one frame. Yeah, I'm done with this demo for now. So yeah, that's basically what happened this last week. Is I thought a lot about what the vector processor is going to be, but I haven't started on that. And I also did this memory testing, and I also massaged the render a bit more. So I like having these sort of like different tasks running in parallel because I like to jump between them and kind of have one in the back of my head while I just chug through some work on the other ones. I think that's a fun way to do things generally. But yeah, maybe we should actually work on trying to debug this this UART and why I couldn't get it to run any faster. So I don't remember why it stopped. I just remember at some point I couldn't double the frequency anymore without it breaking, and I just kind of gave up on it because I didn't think it mattered. For just some debug stuff. But now I would really like to rely on it a bit more. And it might be too that I can't really get it any faster with this setup, or I have to reconfigure the UART chip on here or something. Or maybe I need to bite the bullet and hook up the Ethernet on here, because there is an Ethernet controller, which should give me a lot of bandwidth, way more than I can handle. Because it's kind of a bummer when that's the bottleneck. And we're still going to be hit by latency in any case, because the way this tiled renderer works, it's going to issue some commands to the tile renderer, and then it's going to wait until it's done. So it's like this closed loop, and so we're gonna get hit by that latency quite a bit, or quite often. But it might be also that I could put 3 or 4 of these cores in there to mitigate that, at least for testing. So who knows? But I do have this. The way I tested the UART, I think I've talked about this on the stream before. But essentially what this does is, let's see. Yeah, it sets up again this port, and then it has this little linear feedback shift register, so just some kind of random number generator. And I have one of these random number generators on the PC and also in my RTL test. And the idea is that this, on my PC, I just sit here and wait for the UART to send data. And for all the data that it sends, I check that the values in that buffer are the next values that this LFSR would have produced, which means that the transmitter itself is working. So we validate that. And at the same time, we then send all the data back to the FPGA. And so the FPGA then also has this same checker on it running in a different hardware block. So there's sort of two places where it's checking that this stream is actually working, and then this bidirectional way. So we're testing both the transmitter and the receiver with this test, which I think is pretty nice. Of course, this did not work. Yeah, because I need to run it with COM5. And that'll just hang, of course, until I get the right project running. So let me open that up. Yeah, I also spent a lot of time actually making sure the product or the project's organization was good, even for these test projects. One of the things that I want to see that if I can do is if I can share these IP files between multiple top-level projects. I don't know if I can, but this memory controller got really big just in terms of amount of files. So I would really like to be able to share the IP or maybe some of the clocking modules as well between test projects and the real project. It would also be nice to like take some of these targeted memory tests if I ever end up tweaking some of those parameters and then tweak them just in the test project and have those tweaks already carry over to the larger project. So we'll see if that's something that makes sense. But if not, it's not the worst thing in the world either. Because I don't really care if there's just a crap ton of files in the repo. I just care that we're able to make what we want to make. Getting the thing working is much more important than making it nice and pristine in my head. This is already up to date, but I'm just going to run it again anyway, because I don't trust anything. This takes a minute. I think it takes a bit more than that, actually. Actually, this one's quite fast because it doesn't really need to build much. It has a lot of extra bits here because I just include this one generated.sv file, which is from the Python stuff. So it has a lot of modules in it, but not that many are actually used. The top level code for this is actually tiny. It's this. There's a reset synchronizer. There's the UART transmitter. There's the transmitter. There's the LFSR for the transmitter. There's the UART receiver. There's the receiver LFSR. Just we're using the same module twice. And then there's the actual logic. And all this really does is, I think, yeah, it just checks if there's any data coming out of the receiving end, then it checks that with the next value from the LFSR. And then I think, oh yeah, it shifts whenever we get new data in too. So it's all just kind of automatic. But yeah, just always make sure that the data read matches what comes out of the LFSR. And if it ever doesn't, that's the issue. Then it will throw an error. And then also when this has errored state happens, then it turns off the write request so that it freezes on the PC too. So I can see like how far it got before it errored. And we get that feedback. So essentially if this ever stops working, the whole pipeline will just shut down, which is good. So then by virtue of it continuing to work, we know that it's okay. So I'll load that on there and we should see here. There we go. So now this is running. I don't know if you can really see that, but it's not very fast, as you can see. That's what we want to improve. And if I go ahead and reset the FPGA here, then we can see now there's a bunch of errors. And actually, I don't know why that's not stopping. Probably because we're out of sync here. bet if I do this and then run it, then it'll probably stop. Yeah, because I think what's happening is the new data that it's sending when I do reset like that, still the new data ends up matching with the board itself, and then it's just the PC that's out of sync. So now it's stopped properly, but if I reset that, I think it continues, which is good enough. Again, these tests don't need to be perfect, so this is fine. But yeah, the actual rate that I have here is not a lot. It's, what was it here? Yeah, so about 460 kbaud. And I think you can get this up to a few mbaud on this chip without any issue. You're supposed to be able to, at least. What was it? What was the chip called? FFT232 or something? FTT232? I don't remember. FT2232HL. Just pulling up this data sheet here. Because they've also got this this parallel interface as well that you can do faster stuff with. But then I think you need to configure it differently. See here, it's RS-232, 422, 485 UART transfer data rate up to 12 mbaud, right? So we should be able to get significantly faster than what we're getting now. And that's still going to be pretty slow because mbaud, you divide this by 10 when you're doing bytes because there's 8 to 10 bit encoding with RS-232. So 12 mbaud is going to be 12. Well, I guess 120 kbaud. Is that correct? No. No, 1.2 mbaud is what it should be, which I guess that's actually double this, isn't it? And maybe that is why I wasn't able to clock it higher than this. No, isn't that 3 times this or something? I'm bad at math, you guys. 4608. I hate that these numbers get so like uneven. Oh wait, but this is the baud rate, so this should actually go up to 12 million, by the way. That's why I knew that there was headroom. So I want to actually just try and crank this up and see what happens. I remember having issues with this, but I don't remember why. So we're just going to try and find out. Yeah, calc is a bro. Bidirectional is going to matter for our testing, at least. It doesn't say anything about this because we would essentially say that there's 2 links at this speed. Transmit and receive. I think, at least. That's what it should be. This shouldn't be like double due to being bidirectional. So yeah, this would be the next step up. I just googled common baud rates. This would be the next one. So we need to change it here, and then we need to change it in the different parts of the RTL. I think I have this in a couple places right now. I need to, because I haven't moved the UART transmitter over to Python, even though I moved the receiver. Another reason why I want to do this targeted testing is because then if I want to like move this stuff over to Python, it's easier. Yeah, here's this clock divider, which has like a default baud rate, but I think that that's only instantiated here, and then that's what this actually overrides. So that should be fine. And then the receiver is in UART.py, and this should also have, this actually takes baud rate from here, so that will be in this gen modules, I think is where it is. Need to clean up the files here, but so I think I need to do that, and then I need to rebuild the Python stuff, which I think that's it. I think it's already done. And then now it's building the simulator for later. I don't think that'll work. First of all, in this terminal, I know it won't work. But also I haven't updated all of this. Maybe this is, this is my MinGW terminal. So actually that should be fine. And then all this is because I haven't updated any of the interface after removing the old DDR controller. So I'm way behind on the simulator right now, which is fine. Well, I'll have to fix that anyway. And all these warnings come from my generated Python. Or generated Verilog. I need to generate stuff to suppress these because they're not actually problems. But this is all coming from Verilater, which is kind of nice. But the fact that this part worked is actually the important part. Everything else should be fine. So now if I go into here, this should say it's out of date, and it does. So let's just try that. See what happens if we just generate that. I'm thinking, by the way, for the vector unit, I need to come up with proper names for these again. I remember coming up with color thrust for the rasterizer. Maybe I'll stick with that again. I think that's fun. But for the vector unit for vertex processing, I was thinking to do integer, maybe 4 or 8 integers wide, just straight SIMD. And I was thinking also to, since it's essentially going to be another like CPU, I want to keep it as simple as possible, so I'm going to make it fully pipelined. And I'm thinking also to have it set up where it won't actually detect like hazards, and it won't actually do wait states. So you need to like program it in assembler and do a bunch of no ops. If you need to like use a register that's being written by the previous instruction, for example. I think that kind of thing would actually be really fun for a really small domain like this. And in that way, we actually have a programmable vertex stage, something close to a shader unit for the vertex stage before we actually have that for the pixel stage. And when I was thinking about that design, it might actually be also that we end up with something that can draw pixels potentially a lot faster than the actual rasterizer. But the rasterizer can draw triangles, so there's that. So it might be fun to play with that and see if it actually makes sense to just generalize that to use for the pixel shader as well. Vector blaster, yeah, that's pretty rad. It has to be stupid in 90s like that. You guys get it. Color thruster, the vector blaster. That's great. And then I need to come up with a stupid name for the CPU core too. And then the DMA also needs a stupid name. But I think those are the major components. I don't really think there's the display unit as well. Also needs a stupid name. It's very important that they all have stupid names. So this. Oops. Just try this again. Oh yeah, it was running. Let's just run this again. Reset the system. Yeah, so already 72 bytes, 72 errors. It already sucks. That's annoying. 43 bytes, 43 errors. This always errors. And I have no idea why. No idea why. Suddenly, it just breaks. And the really crappy part is that I don't have proper JTAG on this board, so I can't hook up the chip scope thing that this board has. I guess one of the things that I can do though is that I do know for a fact that the errors are here already. If the PC is detecting the errors, then we already know the data is corrupted before it gets to this point. So we can actually conclude already that it's the transmitter that's fucking up. But how or why? No idea. Maybe we could try to get some insight from looking at the data that actually comes out of it versus what we expect. In fact, that might be a good idea, because then at least we can start seeing if it's something really obvious. Like if it's always outputting 1 or something, which I don't think it will be. I think it's going to be not that dumb. Also, these numbers seem like they're fine for like UART packets, small amounts of packets. Nothing really stands out there. I mean, it is also interesting that we're getting some data out of this. So it's clearly talking to the UART somehow, and we're getting data consistently. So I don't know if it's the receiver or the FTDI chip that I'm using. I don't really know. Exactly, Dark Second, exactly. So fun. But yeah, I do think it's going to be really funny if we end up with a vector unit for vertex processing that ends up being more efficient than the pixel pipeline. But that probably won't be the case, actually, when I think about it, because the pixel pipeline is going to be really optimized for what it's doing. And but the vector unit is going to process more than 1 pixel at a time. So if the vector unit if it has 4 wide vectors, 4 element, if it has 4 element vectors, and it's slightly more than 4 times as slow, slightly faster than 4 times as slow as the pixel unit, then it can keep up, I guess. I don't know. Will be fun to play with. Anyway, the UART, that's the receiver. I don't know why I'm looking at the receiver. That's not going to help me. I also don't really expect much interesting stuff here. Yeah, that's what I was going to do. I'm so scatterbrained right now. I wanted to look at the test program because I wanted to print out when there's errors. I want to know what they are. So the easy way to do this is this. Yeah, so that's not actually doing like a clock divider like the classic kind. It's actually just like a pulse generator so it has an up counter. Whenever the up counter is a certain number, then it resets and then does a pulse. So it isn't actually, I don't think it's that kind of timing. I think if we had those kind of issues, hold on. Then I think the DDR test wouldn't work either. And I think we would have ran into those issues at lower speeds. I mean, it could be. It doesn't work, and I don't know why, so it could be anything, but I don't think that's what it is. Try that. Okay, so this is already interesting because we see we get crap. It is kind of interesting to have the same value over and over again. That's strange. But that also to me says that it's probably related to either we're not pumping out the protocol right, or the little receiver on the FTDI chip is not listening correctly. And I would almost suspect it's that we need to configure the FTDI chip or something. Did I forget in the... Yeah, I did, didn't I? You're right. There, yeah, that helps. That's true. Those are decimal. Yeah, so we're always getting 0, 0 or C0, which is kind of dumb. But yeah, I can show you this clock divider, by the way, because it's not very complicated. It'd be nice to double check that while we're at it. So the clock divider, we have the sort of input clock frequency, and then we have the baud rate. What is this? It has the accumulator width, right? Which I think we can actually lower this when this is higher. I think. You know what? Actually, it might be that this is not wide enough. That could be an obvious thing that could break here. In fact, it doesn't really matter if this is like 32. Let's do that. Let's just try the easy route, see if anything happens without even looking at this further. So essentially what this does, this is the width of this counter. And it does an up counter, and I think it's if this top bit is set. Then... Oh, it's not even that. It just adds this increment, which is this -1 bits. And then every so often, this will overflow into the higher bit. And I think actually the way this is written, it chops that off on the next cycle. Because it takes this -1. So it always chops off that top bit and then adds the incoming value, the same value. And so every so often this is going to overflow and then have that top bit set, which I believe is we use for the clock edge. Yeah, that's the top bit here. And then on the next cycle, that gets cleared. So this just generates pulses whenever this overflows. And this whole calculation here is to detect or to figure out the right increment value so that this overflows at roughly the correct rate. So it's pretty straightforward. And we wouldn't end up with like any timing issues with this. Because I don't actually use this as a clock. I use this to check a condition. So here I have this baud clock edge. And then here I don't use this as a clock. I just, whenever I have the actual clock here, all these states will check for that edge. And again, that edge is a pulse, so they just need to check it once and then move to the next state. So it's fairly straightforward. But maybe clock divider isn't the best name for it. Not sure. But I guess this would make sense. I could probably do the math and figure out if it's actually likely to be this, but if it's so easy to just change it, then I'll just change it. And of course, this was a parameter, so I should technically change this where it's instantiated, but this is easier, and who cares? I want to move this to Python anyway, eventually. And actually doing this part first would be smart. One byte, one error. Is that actually correct? Now we're getting still crap. That's not fun. And it only gets 1 byte, which is kind of interesting. It's always just a couple bytes now, isn't it? We basically always get 0. Sometimes we get something else. This might just be related to me resetting this. That's strange. I did program it. Yeah, that was off screen, wasn't it? I did run this. We can run it again just to be sure. Yeah, so this always just breaks. So if I am holding the reset button and then I let go reset, then it should come out. So already it gets an error and then breaks. It's interesting that it's this slow. That probably means again that the receiver isn't getting the data. So a little sad that just wasn't it, because that seemed to be like maybe that could have been obvious. Although I don't know where some of these magic numbers come from. I don't remember where I got this calculation originally. Maybe I should derive it myself. It's kind of weird that you have like clock frequency, shift right 4. So if you divide this by 4, you're going to get 25 million. I mean, we should still be fairly well below that, but I'm not really sure. We could do some math here. Let's do some math. So at the actual values that we have here, let's see, what did we have for the baud rates? This one. So let's just run through this calculation. If we take the baud rate and we shift it left by a lot, by the way, shift it left by 28. And then we add the clock frequency divided by 32, which which I'll do in another calculator. So if we take the clock frequency, which it is still this, I think, because I'll just type it in, 100 megahertz. Yeah, that's what that is. And then we can right shift that 5. And we get this. So if we add this, and then we divide it by the clock frequency, which again is 100, 0, shift right 4. We can divide this by that. And this isn't that big of a number, assuming, of course, that none of this overflows, which it might. I don't know what kind of width we have for these numbers, actually. If they're 32-bit, then we definitely did overflow it already. Because what did we do? We divide it by this. So if I... Really? No memory? Okay. I guess we can just multiply that again. Then we've clearly gone over 32 bits here. And one of the things we can do here, though, just while we're trying to just do some of this math, is we can look at what the old value was, which was this divided by 2 here. So let's say we could just try to plug in the old values. So we had this number, and we shifted it left by the accumulator minus 4, so that would have been shift left by 12. Just looking for overflows here. This is still 32 bits as an unsigned integer, at least. Or minus, no. Right shift 32. Whoops, that was right shift 5, not 32. Whoops. Right shift 5. Right, and so it would be plus that. We should still be in 32 bits. And then divide that whole thing by the clock frequency. Oops. Shift right 4. And we get 604. Is that correct? Let me do this again, actually. Because it might be that we're just overflowing this. So actually we can do this. Verilog. Yeah, I do so much work in just several calculators now. It's stupid. You know, we can turn up these widths, by the way. The widths of these intermediates, I think. Which might be helpful. But yeah, I just want to do this calc again, just make sure we never overflow at any part of this. So we'll take the old value, which was, again, this divided by 2. Yeah, that's so true. I've really embraced spreadsheet engineering after working at a hardware company. I totally understand why they do that now, because you need to make more informed decisions instead of just trying stuff, because you can't just try stuff. So let's just see here. So this was the target baud rate we had last time, and we would left shift that by the clock accumulator width, which in this case was 16 minus 4 is 12. And here, 3, 4, 5, 7, 8, we're still in 32 bits. And then we're going to add the clock frequency shift right by 5. And then we end up dividing by the clock frequency shift right by 4. Divide this whole thing, and that's a floor divide. Yeah, so we end up with 302. And if we take the what am I trying to say? So I wanna basically get this rate. So if we take 65536 divided by 302, that overflows 217 times. Or 217 iterations of this many cycles will overflow. Maybe that's not the right way to think about it, because it's this many cycles divided by this. And do we get something interesting there? So 302 into... This is the amount of time it takes for one of those ticks. I guess I want to see that there's this many transitions somehow based on this period. So if we take, for example, 1 divided by, we can do this in cycles, divided by 9600, we end up with 10,000 something. So every 10,000 cycles it should do this, right? And that was 302 cycles. So if we took this divided by 302 cycles, we should get around 34. And if we took 302 times 34, am I doing this right? I'm a bit lost here. But I suspect that this is overflowing, and I don't know that this guarantees any width for these. I think it's by default 32. I'll check that out, MS Visser. That's probably where I took that from, by the way. Something like that. I think I found several that do this kind of math. It even says actually that it uses 32-bit intermediate results. You know, another thing that we can do, though, which it probably makes this a lot easier, is we don't need to do this like power of 2 divider, or I mean adder, and then always take that top bit. We could just back out of this approach entirely, which I'm kind of leaning towards doing right now because I don't like this math in the first place. It's hard to follow. And we could just upcount to a particular cycle value and then reset to 0 and then generate a pulse when that happens. Which is not really a bad approach. So I'm going to reset this. And then I think the receiver needs to change. No, that was the receiver. And then where's the transmitter? Here. We'll update that here too, and then we'll update that in the tool here. which is in main. Is it this one? Yeah, it is this one. Just going to copy that value again. I'm just going to back out of trying to understand where this math comes from because I never liked it in the first place. Although we might end up with something similar to that anyway, but let's just try and derive this ourselves. Worst case, we understand that stuff better. So this, what I should actually do before I mess with this is make sure it works again. So I'll build that. And then we'll mess with this. And again, it might still be that then we need to reconfigure the receiver chip or something. I don't think that's the case. So it could be something else that's wrong, but when looking at this code, I did trust it a lot less. But essentially, let's try to work through some of this math here. In fact, I'm going to do this in a spreadsheet to maybe keep this a bit straighter. So what I'm thinking, let's try a new sheet. So I'm thinking that we have, let's zoom in a bit. We have 100 hertz, right? And we have a target baud rate, which is also hertz. I hate when I do that. And so this is going to be, currently it's this. And what we want to do is we want to count how many of these ticks it is in one of these periods. So if the baud rate did this, then we would want to have the counter reach this once per period. I think that's correct. And that becomes fairly easy, right? Because then it's, I guess we can call this the baud period, which would be 1 second divided by this. And so we could do this in clocks, for example. And that should be, actually, we should figure this out in seconds. Because then we can also do clock period in seconds. And this becomes pretty easy because this is just 1 divided by A2, right? 1 divided by this. And this also is 1 divided by B2. And then, so we just need to find out how many of these there are in this. So then I think it's baud clocks, and I think this is just A5 divided by B5. That can't be. Did I do this backwards? I did, didn't I? Because I want these into these, so I need to do equals B5 divided by A5. There we go. 217 of these. That's what I want. And I don't think it matters too much that this rate is a bit off. I mean, one of the things that we can do is, of course, get more precision. And the way we would do that is just scale this, which I guess is what a lot of that other math was doing. So let's see. So So this is how many of these clock ticks we want, and we could, again, if we wanted to do the counter approach, which we could do, let's say we had however many bits. So let's see, counter bits. It might be that we end up back at these numbers again, which I guess that's fine as long as we can come up with a good way to do this. Let's say we did 16 counter bits to see if we can reach what the tutorial had. .13 FF. What's that? I mean, we are quite close, which probably doesn't matter. This will, of course, be a cumulative error, so it's possible that this isn't good, but we'll see. So, oh, off. That's what I meant. Yeah, that's true. But yeah, if we wanted to use this counter approach, then what we would end up with, which I don't think we need, but I guess we could try to target a round number if we wanted to do that. But yeah, now I'm just getting distracted. Sorry. Let's see. So if we wanted 16 counter bits, and then we essentially want the top bit to be set, so we want to count up to the top bit, right? And we want it to happen this often. So I think that's, so then it's like counter target, and I think that's equal to 1 shift left counter bits, which is D8 minus 1. Didn't like the left shift. How do you do left shift in Excel? Well, we could do 2 to the power. That's fine. Excel power. Can we do that? Yes, we can. That's what we should see here, right? That gets 2 billion or something. Good. Then we want it to reach this, because this is with the very top bit set, and so then it'd be this divided by, well, every 217 cycles, or every this many cycles we want it to get to this. Then we would do counter increment is going to be D10 divided by B8. We get 150. Why was this 300? It's interesting, by the way, this is almost exactly 151, and then this said 302. So are we off by 2 somewhere? I think we are, because I think that this clock divider, this actually has 1 extra bit, the way that this is set up. And so if we don't do -1 here, I bet we get exactly what that was. Yes, we do. So that's what's happening there. And then this would be rounded up. Now, what I see here is that if this were rounded up, then we would basically be off the same way we would be here. So I actually don't really see any benefit to doing this with fixed point. Let's do this 32 and actually figure out what that number is, which is kind of fun. Okay, so we basically ended up with the same math, which is good. I can do this as well. This is the number that we generally want here. But I think, honestly, we could just count up to 217 a bunch of times, and whenever it reaches that, then we'll just quit. And I think we're going to end up with a smaller circuit here. So even though we do a whole equality comparison for whether or not we generate this this pulse, the counter should be a lot smaller. So actually, I think we're going to just end up being more minimal the way we did this. So I actually also wonder if there's like floor divide in Excel, because we should be able to. Oh, it's got a floor function. We can even use a multiple, which I guess in this case would be 1. I'm just going to try floor B8. Can I remove that? And then we just get that? That's great. So this will definitely be simpler. So I'm wondering if we can figure out this math in such a way that this gets better. Because I think in Verilog too, you can also figure out the amount of bits that it requires to represent this number, which I think is a string bits. Or is it clog2? Is that what it is? Count log 2 or something? I think that's what it is. I just seen it in some code. I think that's what that does. Turns the ceiling of the logarithm of base 2, right? And so that's if we do number of bits, then we can do, well, we can do the ceiling of, can I do log? Right, and I get the value in the base. So we can do B9. Actually, we'll do B9. And then what's the base 2? So we need an 8-bit counter for this. We get the target and the amount of bits. So actually, I feel like we can do this better. Just seeing how small these numbers are, this should be quite good. I don't know why they did that design. I guess to just tap off that bit, because then it will go up and down at the same time. I guess this takes care of both, but we're going to end up with a smaller design. So I think this is just better now that we derived this ourselves. So go team. And if it fixes our issue, that's even better. So what I want to do first is, again, make sure that this works still. And then we're going to replace it with some math that we do. And we're going to see that it still works, I hope. We got an error already. That's weird. No, still error. What did I break? That is the old bod. That is true. We'll run through the new numbers. Oh yeah, I changed this to 32, didn't I? We need to fix that. So all the same old numbers. That's what we need in this old code. So actually, if this fixes this, by the way, this is a really good indication that this was actually the issue. And then I'm pretty pleased with that. Also, I think I didn't regenerate the code, which also would have broken it now that I think about it. It's that. So one more. So maybe I didn't do that quite right. In any case, I still think we're gonna end up with something simpler, which I'm happy with. Stewart, this one. There. Again, I do want to see this running before we mess with that code, so I'll build that again. But yeah, so if we plug this into the spreadsheet again, if our target baud rate was this, we could do this times 2. And again, the clocks goes way down, so our error rate kind of goes up, but now we only need 7 bits. We can just count up to 108. And I'm guessing this is going to be fine. I guess if we wanted to try and be more accurate, we can try and scale this. But I don't feel like we can be more accurate anyway, because we're going to be locked to this clock anyway. So I'm not sure that it actually ends up getting better. This is not that many clocks, by the way, which is kind of interesting. But 12 MBOD should be well over this. And I don't know if 12 MBOD is still based on these really weird numbers. RS-232 12 MBOD. I want to get the actual rate that ends up being. Hey, Finrog. Thanks for the sub. Appreciate it. Oh, and now I remember who you are. I totally forgot last time. Finrog, which is the fun way to say it, is my fiance's sister's boyfriend, by the way. So make the most fun of him. I don't know where to find these rates. Like if you Google common baud rates, you always get way lower than this. So I want to know the exact frequency. That really bugs me that that's hard to find. See, does this work? Yeah, so now we're working again, which is good. That's the right idea. So let's go 1, 2, 3, 4, 5. We'll make that again, and then we'll go ahead and try to change all this math. Yeah, that's a good point. It probably is just the number. It's worth a shot anyway, right? So I think let's just put that in, see what happens. So it's that, right? 12 million? Yeah, then we're down to 8 clocks. That's fast. Now I don't expect to be able to get this. But I do expect to be able to get higher than what we have now. That's kind of my goal here. But first I want to match what we have now. That's what I want to do first. So let's go ahead and double this again. Oh wait, no. We're not going to double that because we're just going to change this code only in the transmitter and see that we end up with the same results. So let's, first of all, I'm just going to do this. Local param baud clock act width is 16 just to get rid of this. And I think we could do all of this with these like local params here. Yeah, it does work again, Dark Second. I tested that really quick. So did I just did this divided by this. And then this is, yeah, for the power of 2. Yeah, this becomes easier. We actually ignore all these. That's what it was. Just gonna fade that out for my own sake. So yeah, so all we actually need to do is figure out this number here. And is there a good way to do this without relying on these fraction results? I mean, what I should actually do is just hard code this number first. And just see that it works. So if we do this, I don't want to call this the baud clock. I want to call this the baud counter. We can still call this width. And then I'm actually, this is 8, and I'm going to change these to width -1. And then we're going to make clock edge work differently here. So I'm going to remove this. Can I do clock frequency baud? I totally can, can't I? Because these were just scaled by that anyway. Let's just do this. So nice to have you guys, by the way. Yeah, that is exactly what it is. Perfect. Let's just do that then. Good call. Local param baud counter inc. And that's just going to be, like you guys say, clock frequency divided by the baud rate. That is exactly what it is, isn't it? So then this becomes easy. The next one is always going to be ac plus ink. Do I want to start making these? I don't think I make these caps in the other in my other code, so I think I'm going to leave this here. But I do want to do look param bod counter width is c log 2 bod counter ink, right? Because no, it's not ink that we're after here. That's not what we're doing. We're doing bod counter limit target what max was called bod counter max. And then what we actually want to do is 1. So we're going to do this h1. Can you do that like this in Verilog? Sure hope so. Actually, we can test that because when we do make, that actually builds that in Verilator. Yeah, it did not like that. Which is annoying, but we can do 1 here, I guess. I just always like to make those explicit, but I think this is fine. So we'll do this, and then what we want to do, I think we'll just do this. So output, I think we do logic clock edge, and we can do logic clock edge next, which is just the format I'm using here. And so what we can do here is, actually these I also want to call bod counter. So it resets, it does this, and then it also sets, actually we'll order these in a nicer way. So we'll say the clock edge is 0 here, and here we'll do clock edge is clock edge next. And then here we do clock edge next is clock edge. Actually, we're going to make it 0. And then we add 1 to the bod counter. If bod counter is equal to the bod counter max, then we're going to do clock edge next is 1 and bod counter next is 0. I think that's what we want. That's fancy. Oh, what is going wrong here? Also, why do I have 2 of these terminals open? I do not know how that happened. Whatever. What's the issue here? Act next doesn't have. That's true because this should be bod counter next. Okay, so that seemed to build. No. Blocked and non-blocking assignments used in the same thing. Where? That shouldn't be the case. Next, 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 next. Oh yeah, we assign clock edge there. That's true. That would probably do it. Yeah, and I think that seems to have compiled. Yeah, and then it's giving me some issues about bit widths for these. So on line 21, it gives me an issue for the bit width, probably because this. Yeah, equality expects 32 or 27 bits on the left-hand side, but left-hand side varf is 8 bits. And then gives me a warning for the width down on 42. Oh, that's something else. But yeah, I think that's fine. Not going to worry about that. I just want to double check those errors because it takes so long to build. But yeah, we'll try that. This is just a better interface than opening a bunch of calculators anyway. You get into the habit of doing that more. I do think we could make this more accurate if we scale this, because we should at least then represent some of these fractional bits here. But I think this is going to be good enough. And I think it's definitely going to be more reliable than the other code, which I don't think had been tested anywhere near these kind of ranges. And the other thing is, when we get up to however many megabaud, right, then I think this divides more evenly anyway. So I don't actually think we're going to end up with much trouble. 2, for example, 4. So we're even clocks, and then we don't even have to worry about the fact that it's fractional at all. And now, again, we don't really need this to be any faster anyway. It just would be nice for testing, so none of this is mission critical. But I do want to make it as fast as we can to make our lives easier while we test. It's always a noble cause to make your life easier when you test. So that's working, right? That's great. So now we'll go ahead and crank up the rate. And actually, what I should do here is see if we can like sort of visually verify that this rate is more or less what we expect. 7, 8, 9, 10. 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7. That's good enough for me to just like visually get it. So then we'll just go ahead and change the numbers, which should just work. So we'll double this. In fact, if we're going to go up to MBOD, we could, well, I'll double this just to try it, because this is like a standard rate, and then we'll just start trying to adjust it to like the next one up. So the receiver, we also need to be, where's my gen modules.py? Where'd that go? Did I close it? Crap. Oh, no, that's the one I just changed. I keep doing that. So the UART transmitter, yeah, I need to change this one. And then in main here for the test. Is this the right main, by the way? Yes, it is. We'll change it there too. This will also have to be adjusted in the memory test. But we'll deal with that then. So I think that's it. We've set the transmitter, the receiver, and the test, and then we need to go ahead and make again, which shouldn't give us any additional issues because we haven't changed any of the code otherwise. And then we can go and build it again. So we'll build this. We will build this. This probably spits out a bunch of errors because the old test is running at a different rate. But maybe this just works. I'm very pleased if this just works. That would definitely explain why I hit a wall before. And I'm happy that we can replace that old code with something that we actually derived instead instead of something I ripped from some tutorial somewhere when I was learning this stuff a few years ago. That makes me happy. And if this works, we can also verify that really quickly that we did change everything correctly by just changing the baud rate in the receiver on the PC side, because that'll compile basically instantly. And if we get that wrong, we'll definitely get bad values. So that's probably the best way to verify that this actually did work. Because what the problem is when stuff just works, I always like to verify that it's working because of all the things we did. And if we change one of those things, that it stops working. I tend to trust stuff more. especially with this setup where I have to like regenerate the Python stuff and I have to change the value 3 different places. I like to see that if it works, that changing any one of those breaks it. And especially with things like this FPGA development, once all of this stuff is done, then most of the development can all be done with like simulators. We don't really care. Like once this stuff works, we can kind of trust it. Okay, so that didn't work. But we got different kinds of crap than I expected. Got 88. So we're getting interesting values. Not things that are completely wrong. That's unfortunate, actually, because I really just wanted this to work. But yeah, once we've done all this due diligence and like targeted testing with these physical hardware components, then we can kind of just rely on them, or at least the interface that they provide, and know that works. So this is kind of just like the really sloggy part of this that I think it gets easier after all this stuff is done. But unfortunately, this didn't work. And maybe, I don't really know why. It could be that tiny amount. I don't think it is, though, because I can't imagine that that other code would have actually been more reliable in this sense. So if that's the case, actually, then I do want to just run this one as, or I do want to run. Yeah, that is actually true, isn't it? If we double this, that error rate does get to be quite a bit more, doesn't it? Yeah, this is a half a clock off. So then maybe it's actually worthwhile just going straight to 1 megabaud and just seeing if this works. I'm going to do that because that sounds fun. We're just going to see if that works. By the way, if I do this, yeah, so it was able to open it. So I assume that the receiver is able to accept this. Like let's put a really bogus value in here, and I think that this will fail to open. Oh, it didn't. That's a bit concerning. Well, maybe that was still in range, because that would have been 10 million, so like 100 million. No, it still lets us do that. That's concerning. Anyway. Let's just try. So that's all these places. Now, I would normally want to like use signal tap or something on this, but I can't on this board because I don't have the physical connectors and everything, which is frustrating. I could also probably recreate this project again with the old board and tap that way, but we'll try some of this stuff. It's faster to hack on it like this for now, unless we lose a ton of time. But again, worst case scenario, this doesn't have to be any faster than it was, so we'll see. But I'd be surprised if this didn't work, actually. I do know one thing that's actually kind of important that I probably didn't go over here, is that the receiver, I think, actually does 4 times the rate. So this also, I think, needs to be, and this also does that tick counter where I think it just adds 1. Yeah, so this also does, actually this does this, doesn't it? That's funny. So the fact that this does this simple calculation is actually promising for the transmitter doing this, a similar kind of thing. Should point that out. Yeah, and that's actually a good point too, because then that probably means, I mean, I don't think the receiver was generating any errors, because we already had errors transmitting it, because we were able to see that on the PC. So I hadn't even really considered the receiver being more sensitive to this. But if that is the case, then the receiver definitely would be more sensitive to that kind of issue. But we'll see. So in this case, the receiver is going to be this times 4. There's 25 clocks. So that one's going to get more sensitive, I guess, as we try to increase this rate. So it may be that we don't even get much faster than this. Or faster at all, because the receiver might just break. But we'll see. And so if we're able to get this rate better like this, then we'll end up with a lot of jitter. But I guess the rate itself would be okay. Because I'm thinking like 4 times this, or even just 2 times this. Now it's 12.5 clocks. So if we had that sometimes being 12 clocks and sometimes being 13 clocks, if it's half one, half the other, then the rate ends up being the same on average. So I think that would still probably work. Especially because the reason why the receiver super samples like this is just in case there's some of these small rate changes anyway. The receiver has to be a bit more robust to these kind of errors. Where was it? Where was that terminal? I lost it. It's here, and I wasn't running it. Good job, Jake. Yes, this also has a bunch of errors. That's annoying. Although it did get to 4080 bytes before it errored, which is kind of interesting. Okay, so here we got to 343 and then errored in the receiver. Can I run at sub 1 clocks by scaling the input 100 megahertz? Not entirely sure what you mean there. See, this actually gets several bytes here, and then we get a bunch of errors. This actually gets through a fair amount of these before it breaks, which I find surprising. And annoying. I don't really know why it breaks like that. Actually, I think one thing that might make a difference here is that the transmitter actually, I don't think we want to check for this. I think we want to check if the next one is this. So I think we actually want to check for this case. And if that's the case, I think we actually want to do that here. Because then this will be 1 on the next cycle as it resets. I think that's actually more correct. So when the counter is 0 again, then this resets and then we go over. Because I think otherwise we actually had an additional cycle every time. I'm a little surprised it's this sensitive to this jitter, if this is even the issue. But could be. I am running this a lot faster than a lot of these connections, but this chip should be able to handle quite a bit more. But I guess it has to be pretty regular. Anyway, I'll try this. This is something else to try. I mean, we can still, I guess, get some of that back if we scale. If we scale this period, and then still check for the floor value here. Which I guess is what that other code was trying to do. We'll play with it. But I kind of expect this to work. Or rather, I'm kind of surprised that this doesn't work with pretty straight values like this. So I'm thinking if we end up with like 12.5 for the rate, right? Which as soon as we double the baud rate we're going for, the receiver is going to hit this. Then if this actually had one more bit for the counter, then instead of adding 12, it would add, or instead of counting up to 12, it would count up to 25. And instead of adding 12, it would add 12.5 every time effectively. It would actually be able to do that. And so in that case, sometimes it would fire every 3 cycles, and sometimes it would fire every 2 cycles. So it would have a lot of jitter. But I think over time, that rate would still be quite stable. And I think that that's what matters more here. But I could be wrong. Not entirely sure. Yeah, here it also breaks pretty quickly. I mean, it still gets through a number of bytes before it breaks, which is kind of fun, but yeah, this is pretty bad. It feels a bit more stable than it was, actually. Maybe I'm just fooling myself. Yeah, I actually think I'm wrong there. I think it's not any more stable. It breaks very consistently. That's definitely true. And the other thing about the receiver is that it does normally wait that many cycles, like 24 cycles at a time. But it will also reset itself whenever, like, it waits for a start signal, and then it'll reset its internal counter. So it always goes from the start of that. It does some stuff to check if the input was probably bad and stuff. So I would expect this to have been fairly robust. Yeah, I'm not really sure why this doesn't work. That's where I'm at right now. I do think this change I made was correct. The sad part is I don't think it makes a difference. Oh, yo, wait a minute. That's actually one thing I think I made a mistake of here. Oh, no, okay, this is fine, actually. I just piped that into the reset, I think. Okay, that's fine. Then it will actually reset. Whatever it's asked to by this transmitter here, which is what we want. So it's ready to send some data. It'll reset these counters. I guess that could create some jitter. Could try to remove this, I guess. Worth a shot, but I don't think this will fix it. Just something to try. But if this doesn't work, what I'm actually gonna do is just revert these changes, or at least I'll go back to the new version of the code with the old baud rate, and I'll let this run for a few hours just to verify that that's okay. And then I'll put this on the back burner again, which is okay. Not ideal, but it's okay. And then I'll probably read through some of these data sheets and stuff to see if there's anything I'm missing. I always like to scan through data sheets instead of like go to the table of contents and try to find what I need, because I tend to miss stuff. Sometimes there's little notes here and there that are important. Maybe I'm just paranoid about that, but it seems to be the case that that's helpful. I hate these compile times, and they're only going to get worse. Yeah, this is not helping. About the same behavior here. That's annoying. It looked like syntax. The CPU interface thing is actually kind of cool. This chip has a lot of features. I don't know how many of those are even, how many of these other buses and stuff are even wired up on the board. I don't really care because I'm just going to use this as dumb UART. And I could also look at the other kinds of connectivity I can have on the board. It just seems like I'd spend a lot of time debugging if I tried to do Ethernet or something. So I was hoping to just stick with this and make it faster. But that's fine. Maybe I'll come back to this again after I fight with the rasterizer a bit more anyway. That's the big advantage of having many things to do. You can just ignore some of this stuff and do something else that's more fun. Please refer to section error reference source not found. That's helpful. Two independent configurable interfaces, each interface is configured as UART, whatever. I mean, this is interesting too. Greater than 25 megabytes a second over a synchronous parallel FIFO interface. It's also interesting that it says it doesn't support some of these specific rates. I remember it talking about why, but I don't remember what the reason was. Might be worth exploring, actually, to try and use this parallel interface if it's hooked up and configured on my board. I just find this stuff really boring, so I haven't really looked that much into it. But I'm more interested now that I am close to testing a rasterizer. No, I'm trying to reach 1 MBOD. I believe. Yeah, that's 1 MBOD. And none of this is relevant so far. There was, of course, a way to wire up the RS-232 setup, which is what we're working with, but no relevant timing information or anything. Also not relevant, this stuff. purposes for the LEDs. Don't think we're going to find anything interesting here now. Yeah, this is done. Well, that's annoying. Okay, so what I'm going to do is I'm just going to reset these rates to what we had before. And I'll just undo some of these logic changes as well. I still think that the logic in here was correct now, so I'm going to leave that. But I want to make sure that this one is 468, and then the transmitter should also be 468. Again, this is what we had before, so that should be fine. Let's remove this error thing. Whoops. Hate when I accidentally hit F11. So let's see. I think then if I go here, get status, and I don't think anything's really changed except we did the new clock divider logic, which I'm going to keep because it should be smaller. Yeah. Then I'll build that and we'll verify that that works again, and we'll table this. And I'll actually probably just run it for a few hours again, just to make sure it's stable and that I can rely on it, because I would much rather have a very reliable slow connection and feel like that's good than try to push it anyway. But I'm a bit disappointed because I expected to be able to figure this out. I guess another thing that might help debug this is the way I actually wrote this receiver is I had the transmitter in like working because it worked against the PC. And then I set that up in the simulator, in a very later simulator, and then just wrote the receiver against that until it was really robust. Maybe I could do that too, but again, I find it really boring, so I probably won't. Might just stick with this, which again it's going to be fine for the actual system. It's not like we're running into any bottlenecks there. I just hoped to have a bit of a faster link for testing a rasterizer. But again, we can also get around that just by rasterizing less. So I can just draw only some of the tiles for the screen and be able to verify that against the software one. So it's not like this really is any kind of blocker. If it were, then I would just chug through and do the boring stuff. This project still has to be fun. Very important. So program that. And this should break now because it's already sending. So it should be out of sync. Now this should work. Yeah, that's going to work. Okay, well that's heartening at least. I do think we've improved the code Maybe not. I'll run this a few hours and see if it ever breaks, but I don't expect it will. Not at this low rate. And this is also just measuring bandwidth. This doesn't measure latency. But yeah, it does do this 8-10-bit encoding. So I think, again, at this rate, we're getting 46K a second or so, which is a lot faster than the Virtual Boy debugging stuff I made. That's definitely true. But it's pretty slow considering what I'm hoping to achieve with this rasterizer. Because again, from the spreadsheet, tile transfer bytes for one draw call for the entire screen is almost a meg. So this would take like 10 seconds just to transfer that data for the whole screen. That sucks. But I think we'll be okay for testing. Even if it's that slow, I just think it's going to be so cool when this stuff actually is drawing things from the actual hardware. And as long as it's reliable, I'm happy enough. But then if this is all we get, then I'll shelve this for now. And if there's anything I could do on the render or anything quick while I'm hanging out here. Before I go, probably not. I've already been at this for 2 hours. Yeah, Virtual Boy's been on hold for a while. I've been thinking about that project. I mean, I might actually be kind of done with it. Well, we'll see. I would love to get it to 1.0, but I'm just so much more interested in other things. And I think I should just do what I want. Learned a lot from that project, but I have so little interest in doing like a proper UI for that and just all the grunt work it takes to make that proper. And no one's using it anyway, which has a lot to do with the fact that it doesn't have a proper front end. So I understand there's like a chicken egg problem. So maybe I just need to do a few solid blog posts documenting some of the stuff I found and be happy with that. We'll see though. Maybe I get a second wind on that, because there is still, I would still like to do fuzzing tests on the video hardware in particular. I think that'd be fun. I made all that physical hardware for doing those kind of tests, so I feel like it's kind of worth using a bit more, but at the same time I'm not really fascinated by that right now, so it's hard to just be motivated. I don't even think I've been on the Discord in ages. I might just shut that stuff down. As much fun as I have had on that project, it's just not capturing my attention these days. Anyway, we're up to 12 megs that we've transferred with this. That's pretty cool. Would have been nice to have that in a second, but instead we got it a bit slower. I think it's okay if that happens. Used to feel a lot more, I guess, bad about it, but I don't really let myself feel bad about it anymore. W Writer, yes, I use Qt for the top layer UI of the demo tool, the top UI layer. Everything under, like all the logical stuff and all the project handling is all in Rust. But I do use Qt for the top layer, which I'm pretty happy with. Not the fastest development time ever, but very robust and very fast. Yeah, no worries. I don't mind answering again. Yeah, I guess I moved all this math to fixed point as well, which is nice. I forgot I did that. Although I think calculating these fractional stuff right now is done by converting these to floats again and then doing the scaling. Because I think I was doing this 1/over thing. Yeah, I haven't figured out how to do these reciprocals in a nice way yet. That's what this was. Though I don't think this is actually that bad. Not sure. Just something I need to play with that I haven't played with yet. And I basically have to finish all of this fixed point stuff in software first, as I want to verify that it works. It's been a very, very quick development of this stuff, actually. But I think that a lot of that comes down to the simplicity of this algorithm as well. The other thing that I noticed too is when I was reducing, especially reducing the when I was reducing these edge functions to be fixed point, then I noticed stuff that does a lot of blending has a lot more issues with covering pixels multiple times with triangles that share edges. And again, there's a lot of ways around this. I have a to-do here for a left top fill rule, and maybe I'll do that. I was hoping to put that one off. Maybe I'll get away still with not doing that, but need to come up with a good way to do this that also doesn't mess up all of the barycentric coordinates and everything. And I also just want to simplify a lot of this code. Yeah, I don't think, I'm sitting here and I don't think there's anything really useful I can do at this point. I think I'm just getting too tired. So I'll probably head out. But yeah, thanks guys for hanging out. It was fun to try and debug this. Unfortunate that we couldn't really get it any better, but that's how it is. Maybe I'll take another stab at it later. But for now, screw it. Thanks for hanging out, and I'll see you next time.